Hey there, we got a pretty clunky problem. This is kind of hand wavy in a sense, but it all comes together and gives us the results we might want. So we'll just dive in and we'll walk through everything step by step. The statement reads, Part A. By whatever means you can think of, find the vector potential a distance s from an infinite straight wire carrying a current I. Check that del dot A equals 0 and del cross A equal B. Part B. Find the magnetic potential inside the wire if it has radius r and the current is uniformly distributed. Alright, so our goal here is to, quote, form match. Since we know what the magnetic field is from Biot-Savart, we want to form match it with what we need in order to achieve the magnetic field from the curl of the product, i.e. solve a differential equation. So we can form match this with what we know about the field of an infinite wire. Since A is generally parallel or antiparallel minus to I, and is a function of only s, the distance from the wire, we can say that, in cylindrical coordinates, A is a function of s in the z-hat direction. So, we know that B is equal to del cross A, but if we know what B is from Biot-Savart and Ampere's law, and we know what del cross A is in the respective direction that's needed, which is phi hat, that is negative partial with respect to s of A in the phi hat direction, then we could solve for A via solving for this differential equation. So if we integrate both sides from A to S of the magnetic field with respect to ds, then we can solve, and we see that we get a case where we have natural log. Again, we need to have A as a constant since we don't know what it is without initial conditions or boundary conditions, but we will see this come into effect later. So if we check it, the magnetic potential, the divergence of the magnetic potential is indeed 0. And clearly the cross product of the magnetic potential is equal to B since we used it to solve it. So again, for part B, since we have a little difference in our current distribution, we know that from Ampere's law, we can get mu naught I enclosed. Again, we see that B times 2 pi s is equal to mu naught J pi s squared, because again, the wire has cross-sectional area of a circle, and the current density has to flow through it. We see that we get some cancellations, and B is indeed equal to mu naught Js over 2 in the phi hat direction. J itself, though, is equal to I over pi r squared, because again, I divided by the density of the circle, but the circle in this case has a radius r. So we simplify through and we carry out. Now B being the curl of A, we know that the partial with respect to s of A is equal to the negative mu naught I over 2 pi r squared s in the phi hat direction. Again, we'll solve this through by integration, and we see that we get a simple power rule. So, again, here B is an arbitrary constant. Now, here's the thing to note. A must be continuous at R. Okay, this continuity thing has to come up again. We can't just have these field lines disrupting or fringing without the sake of continuity at the surface. So, if we set these two things equal, we see we get some cancellations and such. And we end up with this expression after simplifying the algebra of 2 ln r over A equal 1 minus B over R squared. But what we need in order for this thing to be true is that we need to pick A and B such that this relation holds at the surface. Now we know that if we pick A and B to be R, then we can get the same thing, which is 0. So that's what we'll do. So after we pick A and B to be R, now we can solve for, or write A in terms of outside the wire and inside the wire with respect to the radius of the wire. So that was a mess, but it's pretty useful.